should say something about that. And I should have played with this stuff before now. So I've got a little bit of room here.
Could you like make one more?
I can't make either of them go up until the projector is warmed up.
Oh, wow.
Pretty sure not. So the so the first ring that I want to mention here that's the most familiar is the representation ring of the group GLN. So this is when I've got a group, I can think about all of its representations and make the ERFs into a basis for a ring where the addition in the ring comes from direct sum, the multiplication in the ring comes from tensor product, and the subtraction in the ring I just invent. So I can't actually subtract one representation from another, so I just invent subtraction the same way that one invents the integers from the naturals as equivalence classes of different pairs of naturals. So I'm going to do that. There. So I've got the representation ring of GLN, and it's a ring using the plus and times, but direct sum and the tensor product. And it's got this basis of ERFs, and they're indexed by, GLK. They're indexed by tuples, integers, decreasing. So the ERFs of GLK are they're ERFs of any complex reductive Lie group, or are given by indexed by their dominant weights. The weight lattice for GLK is z to the k, and the dominant weights in there are the ones satisfying these inequalities. Now there's a subring of this where you insist that the lambda 1 down to lambda k are non-negative. And one way to draw such a thing is with a partition of at most k rows and arbitrary width. So this is frequently called the polynomial representations of GLK. And so why is it polynomial? Because if I take a k by k matrix and then I apply my my homomorphism that's going into GL of some large thing. So any representation here, of course, is a homomorphism from GLK to GL of some large space. And in a so-called polynomial representation, the matrix entries here will be polynomials in the original matrix entries. So, for example, sim square is a nice representation where the entries are polynomial. Or determinant is a one-dimensional representation where the determinant is indeed a polynomial in the original matrix entries. Determinant inverse is not a polynomial representation. So some people talk about polynomial representations, and the benefit of saying that is that then you get to work with only with partitions instead of working with more general dominant weights. So I think this is a ridiculous notion, polynomial representations. What are the polynomial representations of SON or SPN? There's no definition except for GLK. So really, I think what one should be interpreting these as, they're representations not of a group, but of this monoid, MK. So MK is all k by k matrices under multiplication. It's not a group. Okay, whatever. And so instead of going from GLK, we're going to go to the endomorphisms of some guy Cn. So if you have one of these, so this is, I want this to be a homomorphism of Lie monoids. I want it to take identity to identity, times to times. I don't have inverses to worry about. I'd like it to be still complex algebraic, that the entries here should be functions of the entries there, algebraic functions, but now that means they've got to be polynomial functions. They can't involve determinant inverse. So if you have one of these things, one of these representations, then you can restrict it to the invertible matrices and say, now I've got this more familiar thing, a representation of GLK. Conversely, what if you have one of these and you ask, can you extend it continuously across the determinant zero matrices? Maybe not. Maybe you get poles. So you can fix those poles by tensoring with the determinant representation. What does that do? It takes, the determinant representation is the one-dimensional irrep of this guy corresponding to 1, 1, 1, 1, 1, 1, 1. So tensoring with that guy adds 1 to all these numbers. If you do that enough, then this will become true. So you get only half of the representations, but it's enough to tell you anything you wanted to know. If you wanted to do computation here, and you only knew how to do computations there, you'd tensor with some powers of determinant. Do your computation there, and then untensor with those powers. So that's why the people who deal with polynomial representations feel okay with themselves that they're actually studying the entire representation ring. Okay. So I'm interested in this one because there's a map from here that says kill partitions that are wider than K. And I'll get down to a ring, wider than n minus K. I'll get down to a smaller ring that has a basis indexed by, so it's now a finite dimensional ring, it's only got dimension n choose K, indexed by partitions that fit inside this box. And that's going to be my picture of cohomology of the Grassmannian of K-planes in CM. So, why does it make sense to do such a thing? You need to prove that if you take the partitions that are wider than n minus K, take the linear subspace of this infinite dimensional vector space that's spanned by those, you need to prove that that's an ideal inside here, so that I can kill it and get myself a ring again. So that's true, that's an ideal. The actual map, I've told you, it's a partition, goes to the same partition. I'm usually going to want to index the Schubert varieties here by words, 0 and 1, instead of by partitions. The correspondence is you read this path going 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1. So this is the correspondence between words 0 and 1 and partitions. Then you need to know that multiplication here goes to multiplication there. And it's enough to know that multiplication by a generator goes to multiplication by a generator. So in the generators that one has for this ring, this is generated by these, where I've got J boxes from 1 up to K. So in 1947, Lisieux observed that the rule, called the Pierre rule, for multiplying here or multiplying there is the same. And therefore, this is a ring homomorphism. Ta-da! It's a really, really unsatisfying proof. It's really not clear, and even now, I'd say it's not fully satisfyingly clear why these two should be related. So the best paper I know on the subject that doesn't just check the Pierre rule, though it does do that. The best paper I know on the subject is this one by Harriet Tumvakis called "The Connection Between Representation Theory and Schubert Calculus." And the word connection is a pun. He takes a vector bundle over, so this Grassmannian comes with an obvious vector bundle over it, the K-plane bundle, the topological bundle. And he uses a UN invariant connection on that, in order to the curvature of the connection and Chern-Weil theory, in order to very naturally define this map, but then having defined this map, it's not clear that it's taking Schubert classes to Schubert classes. And to check that it does that, he says, well, the Peary rule. So I think there's still work to be done in saying why this is working. But I mean, the algebra is very straightforward, Peary and Peary, so both have generators and they generate, so that's something you need to know. Yep.
What are you replacing representations of MK of C with in other types?
Who said I was doing anything in other types?
You said like you didn't like polynomial representations because it doesn't make sense in SPSO.
Right.
Does the alternative make sense in other things?
So
Why is that better
I mean, what do you want to do in other types? We know what this means.
Yeah.
Okay. We might have various things that could go on here.
Okay.
There really isn't, as unsatisfying as this is in type A, I think there's rather less to say in other types. So there is one more ring I'd like to bring into play here, which is the representation ring of Vec. So what does that mean? In general, if you have C some category, then you can think about functors from that category to Vec. And I will call those representations. So the most familiar case is that C is a category with one object and all the so it's got all the morphisms in that category going from that object to itself. And let's maybe say they're all invertible. Then this is the data we're talking about here is exactly a group. And then a functor from this category to Vec, well, this dot has to go somewhere. That's going to be the vector space. And these arrows have to go to match from the vector space to itself. That'll be a representation. So the notion of representation of a category includes the whole theory of group representations. But now it includes this perfectly nicely also. This is MK here I'm thinking of as a subcategory of Vec. So in Vec I have all of these vector spaces and morphisms between them. I'm going to take only the object CK, forget all other morphisms, and so I've got just the endomorphism CK with one object category. That's what I was dealing with here. So here I'm thinking about functors from this category C to Vec, where C itself happens to be Vec. So that's a little bit confusing. Don't get thrown by that. I'm not going to, for example, compose two of these functors to go from Vec to Vec to Vec. It's an interesting thing to do, but I'm not doing it. And still, you could ask, so what are there some functors from Vec to Vec? There's things like tensor to the n that goes from Vec to Vec. So that's going to be a representation. That's not an irreducible representation of Vec. For example, tensor square is sim square direct sum alt square. So this isomorphism writing down here, this is a natural isomorphism in the sense of natural transformations. It's a natural transformation, invertible, from this functor from Vec to Vec to the direct sum of these two functors from Vec to Vec. And I don't actually want all functors from Vec to Vec. I only want ones that are bounded in some sense that's not worth getting into here. But if you do that, then you find out that the irreducible representations are indexed by all partitions. Not partitions that are short enough, but all of them. So, for example, in here, there's a perfectly nice functor called alt k plus 1 that takes a vector space to that alternating power. And if you restrict that functor to CK, you get 0. So that's what's going on from here to here. The map from here to here is taking all of the Schur functors, is the name of this basis, all the functors corresponding to partitions that are too tall and killing them. And then to get here, we take all partitions that are too wide and kill those too. So mainly I got into this because it was a way of sticking in some more representation theory. But now I'm going to get back to this guy and think about the equivariant cohomology of the Grassmannian. And I don't know any way of extending the rest of this story to understand things about ring cohomology. People have been interested in this question for a long time, and I don't think of any suggestion of what sort of thing you should be representing instead of MK, some super algebra, whatever, that would naturally get you some ring with, so what would you want? You'd want some algebra whose modules give you a basis for the representation ring of that algebra, and then a map from that ring with basis to this ring with basis. But somehow you need to have coefficients that are in H star T instead of just Z coefficients. I should have said, as a ring theory statement, these are kind of boring. Like that ring up there, I said it was generated by these alt J's. It's freely generated by them. It's just a polynomial ring. There's not a lot to say about that ring as a ring. It's a ring with basis that's interesting. And the fact that under these homomorphisms, I'm either taking a basis element to a basis element or killing it. All right, so let me be very precise as to what the varieties are we've got. So I've got my Grismanian, and so A planes in Cn. I'll have B minus is the lower triangular matrices. I'll have C for lambda will be an element of n choose k. So this is the set of numbers 1 through n instead of just the number n. And so this is the set of k element subsets. Or I could think of this as words with content k0s, n minus k1s. And then I'll have C lambda will be an element in the Grismanian. It'll be switch these things around all the time here. Which element I mean is the coordinate subspace. That uses those coordinates. And then I'm going to take that coordinate subspace and I'm going to hit it with lower triangular matrices and take the closure, and that will be my definition of X lambda. And in particular, the codimension of X lambda will be, the complex codimension will be the number of ones before zeros in lambda. So the two extremes, the codimension of X 0, 0, 0, 1, 1, 1, 1, 1 is 0, because there's never ones before zeros, whereas the codimension of X 1, 1, 1, 0, 0, 0, 0, 0, where there were n minus k of these and k of those, will be k times n minus k. Because actually this guy is equal on the nose to just the single point, c to the 1, 1, 1, 1, 0, 0, 0, 0. So this is just a point. This is a this is the closed B minus orbit, this guy, on the Grismanian, and the dimension of the Grismanian is k times n minus k. So every one here is before every zero here, and that's what I'm counting in this. So let me give you an example of a Schubert calculus computation. It'll be like the one we did last time, where I said I want to square the class of CP1 inside CP2, and I got some equivariant multiple of the class of CP1 again, plus the class of a point. So the corresponding thing here is I will take x1, 0, 0. I guess the way I'm writing it with these, yeah, this is fine. So I've got x1, 0, 0 is a point in GR2, 3, which is a copy of CP2, and x0, 1, 0 is a line inside there. And the computation we did last time, where we squared a line, and we got a certain multiple of that line, plus the point, looks like this in the in the Schubert basis. So maybe I'll redraw the picture so we see why it's the y1 minus y3. So my coordinates, here's my first and second and third coordinate. And I gotta be labeling other things, so maybe I shouldn't do it quite that way. Let me say, here's my first coordinate, my second coordinate, and, I'm sorry, GR2, 3. Ugh. Do I really care? Oh, and my third coordinate. Here's the Nolan polytope for the CP1, x0, 1, 0. Up here is the guy x1, 0, 0 itself, single point. If you take x0, 1, 0 and you restrict maybe all of this, it's going to be green, blue, black, I'll just put it's going to be black. And if you take this guy, at this point, the restriction gave us that, so that is in fact, it's pointing towards the 1 direction from the 3 direction, that is this y1 minus y3. And here we got 0, and here we got this, which is a y1 minus y2. And 1 second. So I'm getting that wrong. That's the y1 minus y2. All right. So we squared that, and we said that was equal to the original thing. So that times this plus this guy up here. So these two arrows mean I'm multiplying, right? So here this is y1 minus y2. These we already said were y1 minus y3 and y1 minus y2. And here I'm getting y1 minus y2, 1 minus 3 times y2 minus y3. That's what those two arrows are. Pointing away from shoot. I just I'm doing this wrong in my head. There we go. 1, 2, 3. Okay, so I want to give you a rule for computing these products, and this rule will be manifestly positive in a sense due to Bill Graham that I'll get into after I've shown you the rule. So this is due to me and Terry Tao, and it was published in 03, though that was after a while. Oh, right. So in that paper where it appeared, no, that's right. That's what this, which is when you want to multiply x lambda by x mu and expand in the basis of x nus. And when I say basis, remember that's a basis over h star t, not a basis over z. So these guys, c lambda mu nu, are going to live in h star t, which is z bracket y1 through yn. T here, of course, is the diagonal matrices acting on the Grassmannian. Then c lambda mu nu is the sum over puzzles, and puzzles that have lambda here and mu there and new here. And for each puzzle, I take the product over the equivariant pieces. I'll write these guys down in a moment. And if the equivariant piece is in position I and j, we get a factor of yi minus yj. So the ordinary pieces are zeros and ones, and this guy with a 10, and rotations. And the equivariant piece looks kind of like it's made out of two of these, but it's not, because the zeros and ones are in the wrong place. Let me shade this thing in to make it look different from the ordinary pieces. And you're not allowed to rotate this. I guess you can rotate it 180, but I don't want it in the two other rotations. So, for example, let's do this computation. I'd like to multiply 0, 1, 0 by 0, 1, 0. So there's my lambda and mu coming in. And so we already might have seen in the video that there's one way to fill this in with ordinary pieces, and I'll bother to put the 10s here this time. There's one way to fill this in with ordinary pieces and get 1, 0, 0 across the bottom, so that would be the non-equivariant term in this, that the intersection of two lines in the plane is a point. But there's another, the equivariant one, in which we're supposed to get 0, 1, 0 coming out the bottom. And what it looks like, no, what am I doing? Again. So I realized this is the example I usually do. I don't want it to be there, I want to be over here to get my y1 minus y2, but
well, the bottom you did before was 1, 0, 0, and the bottom here is 0, 1, 0. Could that be the problem?
well, I want it to be. I want to get this
I
straight.
want to get the. Oh, right, okay.
I think you just gotta open your box. Do actual puzzle pieces.
Yeah, but I don't have the equivariant pieces there.
Oh.
Yeah, so that's looking good. It's getting me a y2 minus y3, unwanted.
But is that one, is it just, is that a, that's not a equilibrium piece, that one, the time.
This is not an equivariant piece.
You can use tens.
It's got a 10 there. So, I'm more confident of this. Give me 1 second to see what I was doing wrong here. It's exactly because I did this calculation on GR13 when I knew I was supposed to do it on GR23. How embarrassing. So, so there and there and there. So this is the, you should be seeing here y1 plus y2, and here y2 plus y3. So I'm going now from this direction to that direction. It's still y1 minus y3. I'll fix this one up next time. So this and this, you should believe. I'll fix that. I'll fix that up for next time. So let me show you another example. Let's multiply a line by a point, and we should be getting some. So this one, I'm confident to be y1 minus y3 times that point. And we can either do that by this computation, and now straight away we're going to have to put in the equivariant piece. And after that, everything's actually forced. And we get the 1, 0 coming out. But actually, this ring is supposed to be commutative. So we should be able to do the calculation this way. And we find there's two puzzles. There's this one. And there's this one. So this one, the piece was up here, and so it was worth y1 minus y3. But here, the piece is down in the y1 minus y2 position, and here it's in the y2 minus y3 position. So either way you compute, you get the same answer, but for a rather non-obvious reason. There's not going to be a bijective proof of commutativity of this rule. Okay, so I want to give you some insight into the proof that we now have of this rule that generalizes to beyond Grassmannians, not as far as flag manifolds, but to 2-step and 3-step flag manifolds. And before I do that, I want to generalize the problem beyond the Grassmannian to what turns out to be the better space to work, which is the cotangent bundle to the Grassmannian. So remember we had these operators, partial alpha, acting on the T equivariant cohomology of G mod P. And what they would do was take the class of some XW. so I said this in general, but now what I specifically want is GLN by this parabolic, so that's the Grassmannian, and these are gonna be partial I from 1 up to n minus 1. So geometrically where these came from was we took a subvariety of the Grassmannian, or maybe not a subvariety, but somebody mapping in, and we swept it around using a minimal parabolic, and it got a little bit bigger, 1 dimension bigger. If you sweep it around, and you sweep it around it again, it doesn't get any bigger. It's an idempotent operation. So that's what's true set theoretically, that applying partial I twice on the geometrically is getting you something that's no larger. But cohomologically, it's getting you 0. So remember we had this way of computing this guy on the pictures, which was, it was the identity minus reflection divided, or this for alpha, the identity minus this reflection divided by alpha. So this operator is obviously going to kill anything that's symmetric under the reflection by alpha, and because the numerator will be 0. What happens after you've applied it once? This numerator is anti-symmetric under R alpha, and this denominator is also anti-symmetric. And so therefore this ratio will be symmetric, so partial alpha will kill it the next time. So in terms of the calculations we are doing in equine cohomology at fixed points last time, let me just show one of those again. We were starting with the class of a point, which restricted to that point is the product of the weights on the tangent space, and other points was 0. We are applying a divided difference operator in this direction, and we got this guy flipped over, subtracted off, and divide both of them by this, and we got this product now of only 2 things at each of those points instead of 3 things. And this thing is now symmetric under reflection, and so if I apply partial alpha to it again, I'll get 0. So let me say what it's doing on Schubert classes. So partial I applied to x 0 0 1 1 0 1 1 0 1 applies to a Schubert class. There's 2 cases. It'll either be another Schubert class where we take positions I and I plus 1 and we straighten them out to 0 and 1. And that's only if they were 1 0 before. And so 0 if they weren't 1 0 in those positions.